Well, RSA asymmetric encryption system starts out by picking two prime numbers. In practice, these are humongously large primes, but for the sake of this problem, we'll be working with something small as 7 and 11. Once these numbers become large, it gets really hard to be solved with your little calculator, so I had to pick something small. I mean, I even thought about using something like 17 and 23, but already that was a lot harder. So I ended up with something small as 7 and 11. Okay. So you start out by that, and you choose also a public key for exponent. But this is not just the public key. Public key is a pair of n and d, where n is the product of two numbers, right? Yeah. So when that public key is published, open to the public wouldn't know what the two prime numbers were used to create this number. And because this number is so huge, just trying to figure out that those two prime factors is impossible even with very strong computers, okay? Okay, so in our case, the answer is 7 times 11 is 77, so that this one is P times Q, therefore 77 comma 7 is going to be the public knowledge. So you're handing this out to everybody. You don't care if this information is sent out in an unsecured channel that possible hackers are listening, because you're confident that they wouldn't have the computational power to factor the 77 as 7 times 11. Okay, yeah. Okay. Now, usually the RSA scheme uses something called a Carmichael quotient, defined as lambda of PQ is least common multiple of P minus 1, Q minus 1. But we will just use this one instead, because this Euler quotient function is the one that we're more familiar with. Yeah, but if you use the Carmichael, it's slightly easier. Anyways, for P times Q, if you have two prime numbers multiplied, then Euler quotient function is simply P minus 1 times Q minus 1. So that's 7 minus 1 times 11 minus 1, which is 60. Okay. Now, you also need to have your own private key, which is accessible only by you, because you're the only person in the world that knows those two prime numbers P and Q. Okay, so let's try to solve this C. This will be the first question that's a bit tough. Your D is 7, so let's see, C. Since D is 7, we're trying to solve for D, 7 times E congruent to 1 mod 60. Okay, there are two ways to go about solving this. One is to use the Euclid algorithm to find the greatest common denominator, greatest common divisor. But last time when I tried it in class, it wasn't so easy. So let's do it like this. Let's just multiply things both sides until you see some number that's that can be simplified. So for example, 9 times 7 is 63, which is slightly more than 60. So just keep multiplying both sides and come up with numbers that are just slightly more than this 60. And at some point you'll get to the answer, okay? So because In a modular system, we don't have division. Yeah, we can't use fractions. You're only allowed to multiply, so we're going to multiply things. We'll keep multiplying both sides, but we'll multiply numbers that are slightly, multiply numbers so that this thing turns into a number that's slightly above 60. Okay, so 7 times 9 is 63. 1 times 9 is 9. But the reason I like 63 is because 63 is congruent to what number? Mod 60. 63 is congruent to?
3.
3, yeah. 63 minus 60 is 3, right? This 3e is congruent to 9. Mod 60. Hey, and we're already there because now both sides, oh, no. The mod has the property that if this is also divisible by 3, you have to divide every one of them. So when you divide everything by 3, you get E is congruent to 3 mod 20. Okay? Because 60 divided by 3 is 20.
So if you divide by 3, if you divide 3e and 9 by 3, you also divide the mod?
You have to, if this is also divisible by that number. Okay? Yeah. If it's not, then it's just, that's it. Okay? So, well, unfortunately, that happens. Okay. So now, what does this mean? It means that in mod 60, E has several solutions. E could be 20 plus, it could be 3, or 20 plus 3 is 23. 40 plus 3 is 43. Okay? So we need to figure out which one of these are truly solution of C. Okay?
Where did you get 43?
Huh?
How'd you get 43?
Oh, because you keep adding 20.
Oh, okay.
So 3 plus 20 is 23. 23 plus 20 is 43. 43 plus 20 is back to 63, which is in here is 63 is same as 3. So that's what you get.
Right. Is there a reason why you multiplied specifically by 9?
I multiply by 9 because it makes 7 go slightly over 60. If you multiply by 8, then it will make it go slightly above, slightly less than 60. That's also possible too.
Okay.
Yeah.
Bless you.
Okay.
Wait, so how does it go back to mod 60?
Oh, so what does 3 mod 20 mean? It means that if you divide by 20, it's 3.
Yeah.
Can you give me examples of numbers that would give you 3 as a remainder if you divide by 20? 3 itself, of course.
So
23 is another example. 43 is another example. 63 is yet another example, but in mod 60, that's same as 3, so it doesn't yield anything new.
Okay.
So that's what it means. Okay. Yeah, but let's go back and check if any of these are solutions. So let's see, 7 times 3 is 21, and that's not equal to 1 in mod 60. So that's no good. 7 times 23 is, what is that? 7, 21, 14, 161. 161, if you subtract by 120, that's congruent to 41 mod 60. So that's no good either. That's not equal to 1. 7 times 43 is 301, right? And that's definitely, see, 60 times 5 is 300, so that does work. So we see that 43 is the solution to this, right? 43 is the secret key. Okay, that seems to be a little unnerving. So let me show you the other method. Okay? So by trial and error, we found that this is a solution. So that's one way to solve C. Here's another way to solve. So solution 2 for C. Solution 2 for C is just rewrite what this means. This means 7e is equal to 60k plus 1. That's the thing that we're trying to solve, right? And we need to find out the value of e that would make this true. Okay? And if you move this to this side and also replace, write it like this. And that's what's known as the results theorem, which says ax plus by equals to 1, where a, b, x, y are integers. Then the solution of this equation for x and y exists if and only if the GCD of a and b are 1. That's Bizal's theorem. And when you prove Bizal's theorem, you rely on Euclidean algorithm to actually construct solutions of this equation. So we can use the Euclidean algorithm for 60 and 7. Okay? So let's try that. 60 is 7 times 8 plus 4, right? Is that good? 60 is 7 times 8 plus 4. And then 7 is 4 times 1 plus 3. You keep dividing. So this one, Euclidean algorithm says GCD of 60 and 7 is equal to GCD of 7 and 4. That's what the Euclidean algorithm says. But then if to get GCD of 7 and 4, you just do a division. 4 goes 1 times into 7 and 3 is the remainder, and you say GCD of 7 and 4 is equal to GCD of 4 and 3. And then 4 is equal to 3 times 1 plus 1. Then that means GCD of 4, 3 is same as GCD of 3 and 1, but 1 only has divisor 1, so it's 1. So this is a way to show that GCD of 60 and 7 is equal to 1, because this is equal to that is equal to this, so this is equal to 1. That's Euclidean algorithm for finding greatest common divisor of two numbers. However, Bizal's theorem uses this and does some kind of substitution to get some kind of solution here. And the way you do it is you start from 1. You say 1 is equal to 4 minus 3 times 1. And then you look at this and say, hey, this means 3 is equal to 7 minus 4 times 1. You plug that into 3. So that this is 4 minus 7 minus 4 times 1 times 1. And here, maybe it might be helpful to put some colors in here. 60, 7, 4, 7, 4, 3, 4, 3, and 1. Okay. So here, it's 4 and 7 and 4 that are that appear in this side of the story. Okay. Yeah. And what we do is we want to expand this and simplify this without destroying the 7 and 4. Okay, so times 1 doesn't do anything. This is 4 minus 7 plus 4 times 1. And this means it's 4 times 2 minus 7. Is that okay? Yeah. So 4 and 7 must not be destroyed because we're trying so hard to get to the bottom of this to see how to use the combination of 60 and 7 to get a 1, right? Okay, and then if you go look one up higher, it says 4 is, this one says 4 is 60 minus 7 times 8. So you're going to replace this 4 by 60 minus 7 times 8 times 2 minus 7. And what does that give us? That gives you 60 times 2. Okay, and then minus 7 times 8 times 2 is 16. Minus 7. So that's same as 60 times 2 plus 7 times negative 17. Is that okay? All right. So after all this, let's think about what we achieved. So all of this shows us the following fact. We found out that 60 times 2 plus 7 times negative 17 is equal to 1. That's Bezo's theorem. Bezo's theorem just tells us the existence, but it also gives us how to find it by using the Euler in our algorithm and doing some substitution. So we were able to find this out. Okay. Once you find that out, then what you do is you can just do the mod with 60. So we do mod with 60. 60 times 2 plus 7, negative 17, congruent to 1, mod 60. But then look, what is 60 mod 60?
1.
Huh?
Or 0.
Huh?
0.
0, 0, yeah. 60, in mod 60, 60 is same as 0, right? So that's just gone. And look at what it says. It says 7 times negative 17 is congruent to 1. Perfect. Done, right?
The two would be gone also. 60.
Yes, 60 is 0, so 0 times 2 is 0 as well. Yeah. So that's what you get, except that there's something that I still don't like. The fact that negative 17 is a negative number. How do you turn this into positive number?
Multiplied by
No, negative 17 is congruent to what in mod 60?
oh
See, in mod 60 world, you're free to just add 60, right?
you just keep on it. Oh
Yeah.
so,
Just add 60, that's the idea.
oh so it would be 43.
Yeah. Which is the same answer as this one, right? Yeah. But I found that this is not that simple, like plugging in and trying to keep track. I like this better.
Yeah.
Now the one thing that caused us to like have trouble here is the fact that 60 is it has too many divisors. It's divisible by 2 and 3 and all that, also by 5. So whatever you multiply both sides, you end up with some numbers that you end up with some factors. If you divide, you get multiple solutions. So that's what causes some trouble. If you insist, you can do the following. So let me try another way. Okay. So you can just keep multiplying by 7. I don't think that's a good idea, but let's see. If I do multiplication by 7 both sides, that's 49, right? And then you can multiply both sides by 7 again, which gives you 343e congruent to 49 mod 60. And mod 60, if you 60 times 5 is 300, right? So you can subtract 300 from here so that you get 43 times e is congruent to 49. And then multiply by 7 again. So if you multiply by 7, what's that? If you 7 times 3 is 21. Oh, 301. Oh, okay. So that did work. Okay. So 343. And then 300, if you subtract, you just get 1 times e equals 2. And this 343 is same as 43. So that's the solution. So that's yet another way. Just keep multiplying that number. At some point, you're going to get 1. Yeah, as long as this number is co-prime with this number, then if you keep multiplying that number, at some point you get a 1. We got lucky because we hit the solution, we hit the answer in just like 4 tries, or three multiplications of 7. We got it, but sometimes it won't be that lucky. Okay. Now what? Oh, okay. So what is the RSA encryption? Well, people use, so let's say M is the secret message, and this secret can be passed to you by the following encryption, which is you take M to the power of the public exponent mod by N. That's the encrypted message. Okay. But then you're the only person that knows the E corresponding to the D. So what you do is you take M to the power of, so you take this M to the D mod N, and you take the power of E. So this is decryption. So to decrypt, you just have to do M to the D to the power E, and that gives you D times E. What is D times E? D times E is 1, right? So that just becomes 1, M to the first power, which is M. So that's how you recover the original M. And that's recoverable only by you, because you're the only person that knows the private key E. Okay, so let's do that. So let's say in question D, encrypted message is 30. This is 30. Okay. So this M to the D part, that's 30. So now how do you decrypt it? You take the power to the E, which is, in our case, it was 43, right? You have to take the 30 to the power of 43, and you have to do the mod by 77. That's what you have to do. Yeah, this is not so pleasant because it's a huge exponent. But if you, well, let's just do 2 of them, 30 times 30. So what is 30 squared? 30 times 30, which is 900. And then that's congruent to, now we need a calculator. So 900 divided by 77. So when I did 900 divided by 77, I got 11.68. So which means 77 goes into 999 11 times, and then there's some remainder. Okay. So what you do is you can do 900 minus 77 times 11. What is that? 900 minus 77 times 11. That gives you 53. So that's what 30 squared is. 30 squared is congruent to 53 in mod 77. So notice that I'm using equal signs, but there's a congruence here, right? 900 and 900 minus 77 times 11 are congruent because in mod 77, 77 is considered as 0. Right? Okay, then what about 30 to the 4th power? Well, 30 to the 4th power is 30 squared to the 4th power, which is to the 2nd power. But we already know that 30 squared is congruent to 53, so we can replace 30 squared by 53 squared, which is 53 times 53 is equal to 2809. Again, you want to divide this by 77 to see how many times this goes in. And if I do 2809 divided by 77, I get 36 point something. So I need to do 2809 minus 77 times 36. Let's see what that gives us. 2809 minus 77 times 36. I get 37. Again, in mod 77. Okay. Yeah, by squaring the square, you can quickly get to 43 relatively easily. Okay, so you square this again, and that gives you 30 to the 8th power is now going to be 30 to the 4th power to the squared, because 4 times 2 is 8. But we just figured out that 30 to the 4th power is congruent to 37. So we just have to figure out what that is. 37 times 37 is 1369, which is congruent to 1369 minus, how many times 77? 17. 77 times 17, which is equal to 1369 minus 77 times 17. Yeah, that's equal to 60. Now 60, sometimes it's better to write it as negative 17, because that makes things. Now what about 30 to the 16th power? That's 30 to the 8th squared, which is congruent to negative 17 squared, which is 289. So 289 divided by 77, 3 times, so congruent to 289 minus 77 times 3. 289 minus 77 times 3 gives you 58. Again, rewrite that as negative 19. Is that right? Yeah. 19 plus 15 is 77. So these are congruent under mod 77. So 30 squared, 30 to the 32 power is congruent to 30 to the 16th power squared. But 30 to the 16th power is negative 19 squared. And what is that? 381? I think that's it. Yeah. 361, sorry. 361. Let me just make sure. 19 times 19. Yeah, 361 divided by 77. Can go in 4 times, so you can put 77 times 4. And 361 minus 77 times 4, it gives you 53 again. Seems like we're going in circles. Oh, same as that. Huh? Did you just see that? Right? Okay, so what does that mean? That means 30 to the 32 power is congruent to 30 to the square power. And that means 30 to the square, 30th power is 1. Okay, that's nice. So that 30 to the 43 power is congruent to 30 to the, if you, 30 times 30 to the 13th power, right? 30 plus 13 is 43. And because this is 1, you just have to do 30 to the 13th power. But 30 to the 13th power is 30 to the 8th power times 30 to the 4th power times 30. And we know those values. 30 to the 8th power is negative 17. 30 to the 4th power is 37. Okay, so this is going to be negative 17 times 37 times 30. Let's make this into negative 40. No, I don't like that. Instead of negative 17, let's just use 60, okay? So 60, 30 to the 8th power is 60, and then 30 to the 4th power is 37, and 30. What is that? That's 60 times 37 times 30 gives you 66600. Okay. 66600. Okay. Yeah. So hold me this number. And then you divide by 77. That gives you 864. So finally, when you do 66600 minus 77 times 864, you get 72. Okay, so 72 is the secret number.